Now let's talk about parametric equation first before we proceed with vector analysis. This module introduction, I wasn't able to revise this introduction, so never mind that. Our goal is not the semifinal topics but the final topics here, but these learning outcomes is actually correct. Anyway, I will not be solving like the one I did before in parametric equation. This is just a short or quick discussion about these equations. So it says here that if we have a rectangular coordinate, that's why we're talking about this parametric equation being equations that are actually expressed in x with respect to a certain single variable. That's why x is equal to f of u and then y is equal to g of u. You can notice u here being our parameter. So if it is f of t and then that's the other one is f of t as well, so t is our parameter. That's why we call that parametric equation from the word itself, parameter. So if we have this equation or these functions x and y in terms of u, so the slope of that curve for every value of u can be obtained by taking the derivative of f of u. So that's coming from the x the x function, and it should be not equal to 0. So it only means that that's, of course, y prime, starting from our general concept of the slope, that becomes dy over dx based on our Leibniz notation. And then when we try to express this in terms of u, we know that that is dy over du, because if you try to differentiate this with respect to u, that should be dy with respect to u. And that is a complete derivative because it is a pure function of u. And then finally, what you can have here is that we need to simply take the derivative of g of u and then divide that with the derivative of our function of f. So that is actually the expression of our slope. So let's just give a very short example. So if, for example, x is equal to 4, let's just use t instead. And then y is equal to, let's say, e raised to negative t. So we know that dx over dt is equal to 4, and then dy over dt is equal to negative e raised to negative t. Okay, so we know that this x prime of t is not equal to 0, so it satisfies we have a slope. So therefore, the slope of our equation is equal to, we just have to divide the expression from our y and then divide that from our x. Actually, it interchanged. So from our y and then from our x. So with this, we have negative e raised to negative t and then divided by 4. Okay, so this is the slope of that equation, or of that parametric equation. So that's how simple this parametric equation works. That's why I won't be giving you difficult problems here. And now, for example, if we need to find the differential arc length, so this is given by a curve wherein x is equal to f of u and then y is equal to g of u. And then we have some points on that arc. So suppose that this arc length increases, and then of course our value of u increases, then the arc length is the derivative of the function of s with respect to u. So this is the expression of our arc length. So to explain this further, let's have x equal to 8t squared, and then let's have y is equal to 5, let's say, e raised to t. So let me make sure that as t increases, u increases, because it's kind of different story when you have this as if it's decreasing. So with this, we have to take the derivative. We know that that is dx over dt is equal to 16t, and then for our dy, that's dy over dt, that is equal to 5 e raised to t as well. Doesn't change. So with this, we can just follow this procedure. So we know that the derivative of our arc length with respect to t is simply the square root of 16t, and then square that, and then you have to add 5e raised to t, and then you square that as well. So the answer would be the arc length, or the expression of the differential arc length with respect to t. So when you have values of t, for example, you have 5, so you just have to substitute that value to the expression, then you'll be able to get the value. So let's move forward with the curvature, and then the curvature here is that if we have a point P, which is xy, and Q, which is this one is the increment x plus delta x and then y plus delta y. So there are 2 points on the curve of y is equal to f of x. So when a tangent line describes the arc delta s between P and Q, so imagine if we have, let's say a curve, and then I have here 2 points, let's say P, and then this one is this one is the original P, and then this one is Q. So what we have here is that if we have a tangent line that describes the arc delta s between this P and Q, so this is the arc, and then if we have a tangent line here, okay, so that's the tangent line. So the tangent line describes the arc delta s, so this is our delta s actually, this arc length. So the angle that runs through this is our delta alpha, okay, and then the ratio of delta alpha and then the delta s, so that's we'll be talking about the angle here. So the ratio of that delta alpha and then delta s is the average curvature of the arc PQ. So because this tangent line or the curvature is actually giving us the approximate or the average curvature of our arc PQ instead of giving the exact value. So the curvature K at a point P of a curve, so for example, this is the curvature at point K or P. So it is the absolute value of the limit of the average curvature of the arc PQ as Q approaches to P. So in short, this is an approximation wherein we use the alpha, which is the inverse tangent of y prime, which is the slope of this tangent line. And we know that the differential arc length can be measured using this expression. So with this, we can now use the curvature K being equal to the absolute value of the second derivative of y divided by 1 plus y prime, and then square that, and then square the whole expression. Raise the expression to 3/2. So this y prime means that if we have a parametric equation, we go back to this expression, and then that is actually the ratio of g prime u and then f prime of. Now imagine if this is the slope of the parametric equation defined by these two functions. So we can just plug this into this expression for the y prime, of course when you have a value of t. And then for this y prime prime, you just have to take the derivative of this y prime. You can just do y prime prime with respect to t. So that would be positive e raised to negative t, and then just over 4. And of course, we need to make sure that on the second derivative, y prime prime doesn't give us a value of which is undefined. Okay, so with this, you'll be able to find the curvature, but don't worry, I will not give problems that will focus on this curvature. Probably I'll just give some concepts regarding this parametric equation. Okay, so with that, let's proceed with the main topic or the main discussion here, which is actually about vector analysis. So vector calculus is one of the most important, I think, for chemical engineering, because this analysis gives us the idea of how fluid flows, especially when we're dealing with flows that are actually not steady state flow. So before we start with this, I know that you don't have any idea about fluid flow or rheology because you're just starting engineering. So let's just limit all of these discussions about the vector calculus, wherein we have these two fields, the vector and then the scalar fields. So we know for a fact that when we talk about vector, these are the quantities that have both magnitude and direction. For example, if you have speed, and then this speed is actually directed to north, south, or west, we know that that becomes a vector quantity because we have direction. For example, we have mass. Mass doesn't have any direction, so it's a scalar quantity, as well as time. It doesn't have any direction. But when we talk about speed and or velocity, acceleration, when we talk about those things, we know that these quantities are moving toward or away from a certain direction, and then we know that that's a vector quantity. And in calculus, it doesn't have any difference. When we talk about vector and scalar quantities, we need to specify them. Instead of having north, south, west, east, we just use the Euclidean 3D geometry to represent the direction of any vector field. So we have x, y, and z, and any direction at x, we represent that as I hat. For our y, we have j hat, and then for our z, we have k hat. So as you can see, for example, in this expression, a scalar function, which from the start we've been using scalar functions ever since we started the preliminary up until now. So those are the expressions that you can see wherein you just have x, y, z. For example, let's say u is equal to x squared plus y squared plus z squared. This is a scalar function because it doesn't have any direction. But when you see something like an equation that looks like this, you have, for example, let's say r is equal to x squared and then I hat plus y squared and then j hat. So these are vector equations or vector quantities because they have I and j as directions instead of just having this x squared, y squared, and then z squared. Now, to generally write these vector quantities, we use bold I, j, k, and then with a hat. But for faster writing, I will not be using the bold letters. I'll just do some, okay, I hat and then j hat and then k hat. But when we try to type this, it looks pleasing when you have this ijk just to denote that we're talking about the directions, and then for bold letters we actually mean that these are vector quantities, just to give you a quick glimpse of, just for example, you're just looking at the expression, then okay, I know that for a fact that this is actually a vector quantity instead of scalar because it's kind of bold. But the main determining factor is not this bold letter but this direction. Because if it's bold and then you don't have any direction, then that means that it's still a scalar quantity. Okay, so going back with this, what we have first is the gradient. Now, when we talk about gradient, as stated here, this is a vector whose component in any direction is a directional derivative in that direction. This is not a tongue twister wherein you have to say direction, direction, direction. So you'll understand how this works, but the idea is that, for example, if you have, let's say, a 3D plane, and then you have, let's say, an equation, and this is the graph of that equation. So, for example, you set one vector, so let's say it goes through that portion. So the directional derivative from this point, or from this point going to this direction, will always mean that it is the direction normal to the surface of that equation, and then that is increasing in increasing function, and the magnitude represents the greatest rate of increase of the function itself. So it is kind of difficult to explain this in just by saying, because when we talk about 3D, they are actually moving. The vectors are quantities that are actually having direction, so they should be something like moving, or it could be visualized easily when we have arrows moving. So I think I'll be attaching a picture here or whatever just to show you how this gradient works. But it's something like the gradient of Adobe Photoshop. We know that when we talk about gradient, that's actually the movement of the color from one point to another. So this is something like that. We start with a scalar quantity, and then after having the product of the nabla operator and then this scalar function, we have a vector which actually has a direction, which is the component at any direction is the directional derivative in that direction. So let's proceed with this one first. Okay, so this is actually given by the expression, the nabla. So this one is the nabla, the inverted triangle, and then multiplied with the scalar quantity. And then the nabla operator is translated to be something like you take the partial derivative of the expression with respect to x, and then something like this. The nabla operator is something like the partial derivative of any expression you would be writing here. So that's on the I direction, and then plus the partial derivative of y at j direction. So that is any expression here, and then plus the partial derivative of z at k direction. So in this case, since we have a scalar quantity and we're talking about gradient, so the expression we're talking about is this symbol. So this expression, this Greek symbol, is what we call the phi symbol, and we use that to denote the scalar functions that we have. So to make you understand this easier, let's solve for the gradient of this expression. I would also like to emphasize again that when we're talking about the gradient of a certain function, then we know that we'll be starting with any scalar function. So you have to check on that, because if this is a vector quantity, so it has ijk, then we can't actually find the gradient for that case because it's impossible to take the nabla operator and then we multiply this with our expression, which is s. So in this case, this is actually equal to the partial derivative of s with respect to x, okay, and then you add I hat and then plus the partial derivative of s with respect to y, and then you have j hat and then plus the partial derivative of s with respect to x, and then you have k hat. So as you can see, can you imagine this looks something like the total differential using partial derivatives, and that's actually what's happening. You just have to add this ijk as your direction. Now I'll be showing you another way on how to write this ijk without using ijk, but for this case, let's just solve for this one first. So we need to take the partial derivative of this whole expression with respect to x. So we have here 2xy for the first term, and then we have here plus, I think that will be 3zy, okay, and then we don't have any x here, so that's it. And then you enclose this with your I hat. That means that this quantity is actually positioned at the I direction or the x direction. And then we proceed with the partial derivative of the whole term s with respect to y. So that is actually x squared. And then we have plus 3xz. And then this one is zy squared. So that becomes minus 2zy or 2yz. Okay. And that is enclosed with the direction at j. And then we add the last one for z. So we don't have any z for the first one. But for the second and the third one we have. So we have here 3xy, I think. And then minus we have y squared, and then we have k hat. So in this case, we have this term at the x direction, this one at the y, and then this one is at the z direction. So you don't have to like simplify this further because you can't do anything about it. You don't add these two because they are on the different direction. Only the expressions on the inside of the parentheses you can actually simplify that if you can, but you don't perform operations on the outside of that parenthesis. So this is the answer for the gradient of s. That's just a simple way. It's like finding the total differential using partial derivatives. Now this can also be rewritten in terms of the vector notation that we can always use in physics. So delta s is actually equal to this expression. We have 2xy then plus 3zy, so you just have to like put a comma. So that means that I'm taking this first term at the I direction. But you don't have to write that. Okay, so comma, and then you write x squared plus 3xz minus 2zy. You can also use this one. Just can add parentheses, so comma, and then 3xy minus y squared. So you can also add comma, and then you enclose that with that. It's not actually the less than and then the greater than sign, but it looks like one. But the less than is something like it's more pointed, but this one is not actually pointed. It's something like a modified bracket that we use to represent vectors. Okay, so that's the other way of writing the answer. And remember, when you do gradient, you should always get a vector quantity. It's a must. So when you try to do gradient and then if you forget, for example, this I and then jk, so you'll be able to simplify this further, but of course that would be wrong because you have to indicate ijk because this should be a vector quantity. So now let's have the second example. It says here that we need to take the gradient of u, so that's the nabla operator multiplied with u, and then u is this expression. And we also have the answer right here, and let's see if we could get the answer. So let's rewrite this delta u, the nabla u, that is equal to the partial derivative of u with respect to x at the I direction, and then we have the partial derivative of u with respect to y at the j direction. Then we have the partial derivative of u with respect to z at the k direction. So in this case, we have the total differential for each partial derivative. So let's start with x. So that's e raised to negative 3xy, and then the derivative of this is negative 3y. Okay, and then we proceed, since it has x, so we have plus sine h. So remember, this is positive because it is a hyperbolic function, so x plus y squared, then multiplied with 1. So we have minus, and then since we have z here, so we need to take the derivative of this one, so minus 1 over z over x, and then we multiply this with the derivative of z over x, which is actually, that is z x raised to negative 1. So if you try to differentiate x to the negative 1, what we have is times z and then times negative x raised to negative 2. Okay, and then this is enclosed to I hat. Okay, then for the next term we have y, so we also have e raised to negative 3xy, but in this case we have times negative 3x, and then plus sine h of x plus y squared, but in this case, since it's y, so we have 2y, and then minus, so that's minus 0 because we don't have any y here, so we can now enclose this to a bracket or brace, and then just have this j hat. Let me clean this up. So that's j hat, and then we add the last one, that's for z. So the only z that we can see here is this one actually. So we have negative negative 1 over z over x, and then we multiply this with the derivative of z, taking x as our constant. So with that, that's 1, and then that will be 1 over x. Okay, so with this, we multiply this with k hat. Okay, so with this, we can now simplify for the gradient of u. So that is equal to, I think that would be negative 3y e raised to negative 3xy, and then plus hyperbolic sine of x plus y squared. And then we have, so this is z over x, that becomes x over z. Z can be cancelled out here, and then if this is at the top and this one is at the bottom, we could say that that will be left out with positive 1 over x. So we have positive 1 over x, and then that is I hat, and then plus we have negative 3x e raised to negative 3xy, and then we have plus the hyperbolic sine of x plus y squared multiplied with 2y. So let's just move this a little. So we have 2y and then finally, to end this expression or the answer, we have z and then over x. So this becomes x over z, and then this one is cancelled. So we have minus. We actually have minus 1 over z here. So minus 1 over z, and that is multiplied with k hat. Okay, so this is the final answer for the gradient of the expression written above. Okay, so I hope we have the same answer as I think we do have. So this is the final expression of the gradient of u. You can also write this in terms of the vector notation. So we have here the this modified bracket here and the pointed bracket. I don't know how it is called. And then you just have to list them in terms of comma. Just make sure that I, j, and k comes. Just make sure that I comes first, and then j, and then lastly k. You can't interchange them because that's actually the notation of this vector writing system. So now let's have another one. Now for this problem, we're not asked to find the gradient, but we're asked to find the directional derivative for f(x,y,z) for a direction of v 2, 2, 3. So when we talk about the directional derivative, we're actually finding the gradient itself. But the only difference that when we talk about this directional derivative, the direction is actually not ijk, but it is specified from this v 2, 2, 3. So imagine if you have a point at 2, 2, 3, and then we start to like finding the derivative with respect to that direction. So we need to substitute this on our direction. And to start with that, we need to find a way wherein ijk, the resultant of this direction would be equal to 1. But if you try to like find r here, we know that that will be equal to 2 squared plus 2 squared and then plus 3 squared. So that's simply ijk having the numerical equivalent. And in this case, that will be equal to square root of 17. Okay. So with this, if this is equal to square root of 17, we know that for each distance to be unit vector, we just have to like divide all of the each distances, numerical distances with the resultant. So we have to like convert this to 2 over the square root of 17, and then this one is 2 over the square root of 17, and then this one is 3 over the square root of 17. And then with this, we know very well that if we try to take the resultant of this vector, this becomes already a unit vector. So r would be equal to 1. That's actually our main goal in this case. So that's the first one that we have to do. We need to translate this direction in a unit vector. And then finally, we need to take the directional derivative. So with that, we start with finding the gradient of f. So with this, the gradient of f is equal to, we start with partial derivative of this expression with respect to x. So that is negative yz times x raised to negative yz minus 1. And then we skip with this second term, then we have plus cosine inverse of 3z. Okay, hyperbolic cosine inverse of 3z times x. Okay, and then we close this with our I, and in this case, it's no longer I. We need to substitute this with our direction, which is coming from the unit vector. So we have 2 over the square root of 17. So you might be getting confused. You don't use this value itself because that's the direction from the origin, taking in consideration the Cartesian coordinate, the 3D Euclidean plane. We need to actually convert that in terms of unit vector. So this is the correct direction. And then plus, we add the expression wherein we take the partial derivative of f with respect to y. So this one becomes a variable. So we have x raised to negative yz. Okay, and then we need to just have to take the ln of our base and then the derivative of yz, which is actually equal to z. Okay, or it should be negative z, so we add negative here, and then plus. So for the second one, we have a constant exponent and then a variable that is a base, so that's like power rule. So we have ln of z and then times y raised to ln of z minus 1, and then we take the derivative of y, which is simply y. Okay, so with this, we enclose this with bracket, and then we multiply this with the directional the distance or the direction itself. So that's actually the numerical distance would be 2 over the square root of 17, this one. And then lastly, for z, we have x raised to negative yz. So basically, this x raised to negative yz is, we're taking this x as a constant. So we have to take the ln of x, and then the derivative of yz is simply negative y. Okay, and then plus, we have y raised to ln of z. And we know that if z is a constant, the variable, then y is a constant. So we just have to use u to the a. So that's y raised to ln z, and then we take the ln of y, and then we differentiate z, so that would be equal to 1 over z. Okay, and then finally, we have here the inverse cosine of h and then 3z. And we know that the inverse cosine, hyperbolic cosine, we know that it's not a reciprocal function, so that should be positive. And then that's it. It should be positive. So we have plus. So x is actually included because it's a constant here. So x, we multiply it with x, and then we take the derivative of hyperbolic inverse of 3z. So that will be 1 over the square root of, and we know that that should be u squared minus 1, so that becomes 9z squared minus 1, and then we take the derivative of 3z, so that will be times 3. Okay, so with this, we multiply this with the directional value of k, which is actually equal to 3 over the square root of 17. Okay, so this is kind of long, but it's not really that difficult. So the gradient of f is equivalent to, just simplify this, and then you'll be able to get the same result here. Just have to multiply this, and then this becomes 3x. I think this becomes over z. That's just how we simplify this. Okay, so that's it. That's the directional derivative. And then we move on to the next question. From number 3, if a point exists at 1, 4, 3, what is the value of the derivative? So we need to find the value of the derivative. And then what is the directional derivative of maximum magnitude, or the greatest rate of increase? So if you could go back to our discussions here, this is the expression of our directional derivative. So you just have to find this value wherein you don't have to give the numerical value of the direction as referred to the vector, unit vector. You just have to take the resultant of each of them. So it's like doing what we did here in R. So we start first with the first question: what is the value of the derivative? So if you already have this directional derivative, what you have to do is to substitute the value 1, 4, 3 from the equation itself. So in this case, if you have 1, 4, and 3, you just have to substitute the values of this. X is equal to 1, y is equal to 4, and z is equal to 3. And then plugging all of these values to this expression. I won't be showing you how it is done. It's just a direct substitution. You could just, for example, you have negative times 4 times z, so times 3 times x. There's a negative 4 times 3 minus 1. Now, I will be only showing you the hyperbolic cosine in the calculator because I believe that you already know how to find the logarithm and all this exponential function in your calculator. And this is not actually a high school problem where I will show you how to substitute all of these values. There are very many, so do it on your own now. But for this case, the hyperbolic cosine, I'll be showing you how. And now if you look at your calculator, you can see here, I hope you can see my cursor, that means hyperbolic, so you can just press that. And then, of course, before you do that, make sure that you're actually having the radians mode. So if not, you go to mode and then you do something like, shift mode, and then you press radians, and that's number 4. Okay, so you press hyperbolic functions, and then you'll be given with all the 3 main hyperbolic functions and its inverse. So what we have to do is to press hyperbolic cosine of h, so that's 5, and then we need to substitute 3z. So evaluating that, we have 3 times z here is 3, so it's like taking the hyperbolic inverse cosine of 9. So this is the answer. So this is 2.88727. This portion is only 2.887. So you do the rest, substitution, and then you should be able to get a value that is equal to this one, 0.8261. Okay, so now let's have the maximum magnitude of the directional derivative. So I'll be showing you how it is done, but the main idea is just the same as the directional derivative, only that you don't have to multiply it with 2 square root of 17. You just leave it right that. So for example, we have the nabla f, so that is equal to, I'll be substituting all the values. So we have, for example, that's negative, let's say my x is a and b is y, so that's b, and then c is z, so c raised to times a raised to negative yz, so that would be bc, and then minus 1, and then plus the hyperbolic cosine inverse of 3z. Okay, so with this, let me just give the value. B is our y, so that is 4. Okay, and then c is our 3, and then a is actually 1. So therefore, that's it for the first term. So I have negative 9.11279. So that's negative 9.11279. Okay, and the best thing that you can do here is to shift store that answer to any letter that you're not using, because I think that that's the best way to store the exact value. And then, of course, you write I hat instead of using square root of 2 over 17, because we're talking about the maximum magnitude here. Okay, so going back, let's have the second expression. I think I mistyped this answer. It should be something like 112729. Okay, 112729. Okay, so let's proceed with the next term. We have, so you press AC, and then you have negative alpha x, a, negative a, and then raised to negative bc, so that's 1.25954. So that is plus 1.25954, and then that is j hat. Okay, and then finally you do the same with k. So for your k, it's the longest expression, I think. Okay, but I just have to follow through this. That's negative a, okay, so finally we solve for this a, b, and then c. So we'll be able to obtain the value of your k component. So that's 2.45457. So 2.45457. Okay, I actually forgot to store the two previous values. So the value component for j. So let's just store this. Let's just store this one, and then let's just copy this. I hope I get the same result. So we need to find the resultant. It says here that you just have to take the absolute value for that. So that's actually taking the resultant of this value. So whenever you have something like a vector and then you need to find the resultant, you just have to take the square root. You just have to take the square root of each component by squaring all of them. So my writing is already messed up. So that's square root of this one. So that's negative 9.112729. We square that, and then we add 1.12594. I think that's 1.2 only. So 1.25954, and then squared, and then plus 2.45457. And then you square that. Okay? And finally, you'll be able to get the resultant, which is actually equal to, let's do that here. I hope that rounding this second term will not give us a really different value. That's squared, and then plus, it's not actually a, it's actually, I think I stored that at D, and then the other one is at F. Alpha F squared. Alpha F squared, because the one is supposedly stored in E. Anyway, so we have, that's it. We have 9.521. Okay, we also get the same answer. So that's 9.5212. Okay. So that's it for our answer, and I hope you were able to get this TF. I didn't show you, but in this Nabla F, I hope you would be able to see what went wrong in your solution. Now there is another way where you could just avoid doing this squared. We can have this mode, and then you can go to vector, and then just press vector A, and then we have 3. So that means that I have 3 columns and then 1 row. You can just write the expression. So in this case, I'll be writing D because that's the one I stored for the first component I. And then for the second one, I'll just be typing it 25954. Okay. And then for the last one, I think that's alpha F. So that's it. I've already written that in terms of A, B, and C. And then you press AC. Okay. So you've already stored that. And then you press Shift. And then you go to Vector. Okay. So with this, you're given with the dimension versus the data. If you want to change your data, you press 2. And then you have 3 options here, vector A, B, and C. And remember, we chose vector A. And this one is the vector answer. This one is the vector product. Okay. So what we want is the vector A. And then we need to find the value of this vector A. And then what you have to do is to press Shift and then you press absolute. That's on the hyper, this button type. So if you have vector A and then you press the absolute of that vector A, you'll be able to get the resultant, which is 9.512. So that's the other way of finding the resultant if you forget to how to do the resultant. But that's just an easy way. Just do something like the absolute of VCTA. And as you can see, why is it absolute? That's actually the symbol that we use here. That's the absolute value of your gradient F. So in this case, this is the answer for the maximum magnitude of greatest rate of increase. And as you can see, this is a very high answer compared to this 0.8621. Okay, so I think that gives you a very profound knowledge in gradient examples. So let's have another one here. We need to also find the directional derivative, and we need to find the directional derivative of maximum magnitude. Now, I will not be showing you on how we could like substitute each of the values and then do something like that before, but I'll just show you how we can derive the expression and then you just do the substitution. Okay, so first of all, this dx, dy, and dz is not given like this one, but we can deduce like this. Where's that one? This one, the direction is actually given here. It's not actually given like that, but we can deduce something from this. If we let, for example, if we let dx is equal to 1, we know that dy is also equal to 1, and then dz would be equal to, I think that would be 1/2. And if these are the values of x, y, and z, so that's something like the I direction, the j direction, and then the k, we need to make sure that this is actually a unit vector. And to do that, we have r is equal to the square root of 1 plus 1 plus 1/4, because that's 1 squared plus 1 squared plus 1/2 squared. So with this, r would be something like equal to square root of 9/4, which gives us 3/2. So 3/2 is not equal to 1. So with this, we need to convert this direction in terms of unit vector. So let's just assume that we have v as our direction, and then let's have, for example, that's 1 over 3/2. The other one's 1 over 3/2 again. And then for 2z, we have actually 1/2. And then that is divided by, so that is divided by 3/2. So with this, the unit vector of the direction becomes 2/3. That's also 2/3 for the j direction. And then for the k, we have, I think that would be 1/3. Okay, so with this, finally, we can now solve for the directional derivative and of course the maximum magnitude. So we have the expression. So I cannot actually give you this nabla operator of something like this because we don't have any expression right here. So let's just copy. We take the nabla operator and then we multiply that with our whole expression so that we can give the correct value or the correct expression in our case. So that is equal to, we take the partial derivative of x first with respect to, the partial derivative of this expression with respect to x. In this case, we have x e raised to xy, so that's product rule. But before we do product rule, remember that this is power rule. So 2 times x raised to e raised to xy minus ln of y raised to, is it z or 2? That's actually squared. So squared So therefore, we don't have any z. But we do have this direction, so it's like you don't have this z in the term, but it should be included. So that's the power rule, and then we differentiate that. So I think this will be product rule. So x times e raised to xy, and then times this would be y, because the derivative of xy is simply y, knowing that y is a constant. And then we have plus e raised to xy times 1. And I think we have to close this because ln y squared doesn't have any x value in that x expression. So we have I hat in this case, or you can also use dx, can also be that way, but I'm just I prefer this I hat. And then we have plus, we add 2 times x raised to e raised to xy minus ln of y squared, and then by doing this, we also have to multiply this with the derivative. So x is a constant, and then e raised to xy, and then times x, and then this one should be differentiated, so that's 1 minus y squared, minus 1 over y squared times 2y. Okay, and I think we're done with j. And then for k, we have 0k. You don't have to write 0k because we know very well that that's actually 0. So therefore, the the gradient of this expression is equal to okay, so I think this is the directional gradient. That is the best way I can simplify that. And then if you're asked to find the directional derivative, the point is negative 1, 1, 2. So if you let x is equal to negative 1, y is equal to 1, and then z is positive 2. So z is equal to positive 2, and we know that if you substitute all of this, then you should be able to get df, which is equal to 0.8006. So df is equal to 0.8006. Okay, and then finally, if we need to find this maximum magnitude, we go back to this expression, and then you don't have to multiply 2/3 to this expression, you just have to substitute this xyz, and then with that you take the absolute of the vector. So let's say take that absolute, and then that would be equal to the nabla of f, the absolute. So that would be that will give you 1.2008. And I hope that you've understood how I did that on the previous problem. It's just the same concept. You just have to substitute xyz in an expression, then leave this as if it's ijk by doing this, and then you take the absolute value of that vector or the resultant. So you'll be able to get this expression or answer. Okay, so I think that's all for gradient. We also have another one here. Let's have this. So the last problem for gradient is this problem. Let's have this one. A Newtonian motion exists as the velocity profile v is equal to u squared minus 60 plus 8u. So that's actually the scalar expression, and then we need to determine the gradient assuming u is in the I region and then t is in the j region. So in this case, it doesn't have x and y on our 3D Euclidean plane, but this u and then t, which is actually v. So that's kind of different letters or variables. So what we have to remember is that u is on the I and then t is on the j region. So if you take the nabla operator for u, we have to differentiate, v, should be v. So we need to differentiate those partially by taking the total differential. So that's nabla of v, that is actually equal to 2u. Okay, so 2u plus 8 to the u and then ln of 8. Okay, and then this is actually the I direction. Okay, and then for our j, we have plus, so that will be negative 6, I think, and that's the only value for j, so that'll be j hat. Okay, and then finally for our gradient, so we have 2u plus a to the u ln of 8, that's on the I direction, then minus 6 for the j direction. We don't have any direction for k. So I think that's it for this problem. That's a very easy one compared to our previous problem. Just to show you, this problem is intended to show you that other variables exist in the 3D Euclidean plane. It's just that it's not always x and y.